Welcome back to my classes on fundamentals of electrical circuits. Now we have started AC circuits, and I am still trying my very best to see that you're convinced that AC circuits are very simple, so long as you know a few principles, a few rules, and a few conversions, etc., which you can carry with you anywhere and be able to do any kind of AC problems. In fact, AC problems are very popular, and in most of the related subjects, the knowledge of AC is going to be very useful. Okay, so these are of course fundamentals when you're talking about circuits, and it is always the fundamentals which are going to help you in your journey through electrical engineering or related branches of engineering. Okay, so here today we look at essentially mostly resonance. Not this session will be dealing with mostly resonance and some frequency related problems, and perhaps some others as well, but I have named it as resonance and frequency. Okay, so let's see if the first problem has something to do with resonance. We see a circuit with Im sin omega t. I hope we remember that Im is the maximum value and omega happens to be the frequency in radians per second. And this current now divides into 3 and flows through the resistor R of 10 ohms, the inductor of 10 millihenry, and the capacitor of 10 microfarad. Okay, and what is asked is that the figure shows an RLC circuit with the sinusoidal current source at resonance. Okay, so at resonance, the most important aspect happens to be that be it parallel resonance or series resonance, the circuit becomes essentially purely resistive. Okay, and so what is asked is the ratio of IL and IR. That is the ratio of the magnitude of the inductor current phasor and the resistor current phasor. Okay, so we have, since both are phasors, division by root 2 is applicable for both. So we just need to find out IL by IR. Okay, so what is IL by IR? Okay, so the admission of current will definitely depend upon the impedance values. Okay, so here it is admittance. Why? Because the current has to be admitted. So it is going to be the admittance ratio. So IL by IR is the same as equal to the resistance divided by, the ratio will be the same as equal to resistance divided by omega L. So what we don't have here is omega, and it has been already said that we are having resonance. So omega is automatically equal to 1 by root LC. Okay, so what is L? It is 10 millihenry, and what is C? It is 10 microfarad. So if you take the ratio, it comes to the same as equal to 1 by omega is equal to 1 by root LC. It becomes the same as equal to 10 raised to 9. The 10 raised to minus 3 and 10 raised to minus 6 go to the numerator. So 10 raised to 9 divided by 100. So it is going to be 10 raised to 3 into root 3. Okay, so we'll retain it as such. Okay, and now we'll write out IL by IR as equal to R by omega L, as was mentioned earlier. So it is equal to 10 by 10 root 2. So 10 and 10 cancel. 1 by root 10, or 10 by if you divide and multiply by root 10, it becomes root 10 by 10, or in other words, it is 3.16. So root 10 you had better remember as equal to 3.16. So divide by 10, it makes it 0.316, and only 2 decimal places are required. So 0.32 is a good answer. Okay, so this is how we can easily use a resonance and the phenomenon of resonance to solve problems. Okay, and also the fact that the current ratio is now going to be proportional to admittance ratio, or in other words, IL by IR will be equal to R by omega L. Okay, moving on to the problem number 2. Here it doesn't look like a resonance because current I is shown and the voltage across a similar set of elements. That is, we have resistance YR, so admittance is what is given perhaps, and then again YL and YC. Okay, so all the 3 admittance values for the current is given, and also the voltage across and accordingly the voltage developed across each of these branches, which is equal to 10, which is equal to 10 angle 0. So again, resonance is indicated perhaps because we are seeing that the voltage is in phase with the voltage seems to be in phase with current, though the current is not mentioned. Okay, so it may not be resonant. Let's see. Let's read the problem further. In figure, the admittance values of the elements in Siemens are, so YR is given as equal to 0.5 plus J0. Okay, and YL is given as 0 minus 1.5, and YC is given as equal to 0.3 respectively. The value of I as a phasor when the voltage E across the elements is 10 angle 0. Okay, so very easy to rather than just like we multiply current to impedances to get voltage, the voltages can be multiplied by the admittance to get the current. Okay, so the relations, those relations, what to use is very easy. It's very good to remember. So now we have 10 angle 0 multiplied by the admittance of the resistance, which is 0.5. So we have one component as equal to 5. Okay, so the real value will not change. It will always be dependent upon the resistance. So we are on the resistance, in this case the admittance. So there are two answers with 5, B or C, B or D. So we might be choosing one of them. Okay, so a glance towards the answers is always good. Okay, so it will tell you as to how to solve as well. Okay, now the admittances are opposite in direction with respect to the inductance and capacitance. So the resultant will be their difference. Okay, so what do we have here? We have YC as equal to 0.3 and YL as equal to minus 1.5. So the net result is going to be minus 1.2. Okay, and definitely the inductive reactance is larger. Okay, so inductive reactance is larger. So let's see what the voltage is going to be. So that's 1.2 minus J 1.2 minus J 1.2 into 10 is going to give us minus J12. So 5 minus J12, which is answer D, is going to be right. Okay, I hope you have noticed that the current is now is not having an angle 0. So there's no resonance here. We just use there's no resonance. If there had been a resonance, the voltage and current would have been in phase. Right now we are having an angle as described by a resistance equal to 5 and not a resistance, the real portion as equal to 5 and an imaginary portion as equal to minus J12. Or in other words, the resistance creates the real part of the current, and the reactances together creates the imaginary portion. A third analysis that comes directly from here is that we can see that the answer is 5 minus J12. Okay, we just multiplied and we got the answer as 5 minus J12. Okay, this is telling us that there is a negative angle, or in other words, the current lags the voltage. Why? Because the inductive reactance is larger. Okay, so now let's move on to the next problem, where we have a similar such question, where we are having a sinusoidal voltage source V feeding a resistor, inductor and capacitance, each of them having equal numerical values, that is 5 ohms for the resistor, 5 Henry for the inductor and 5 farad for the capacitor. Okay, so the question is that for sinusoidal voltage source V, the current I is in phase. Immediately when current is in phase, as was mentioned for both the two problems, both the problems mentioned earlier, we are having resonance. Okay, or in other words, the effective resistance is, the effective value of the impedance is only 5 ohm resistor. Okay, and what is asked is the current I is in phase with voltage V. The ratio of the amplitude of voltage across the capacitor. Okay, so when you are talking about the voltage, the impedance is going to be important. Okay, and divided by the amplitude of voltage across the resistor. Okay, so now we see voltage across the resistor. Okay, so we have so now it's going to be 1 by omega C divided by R, or 1 by omega CR. Okay, of course we need to find omega, so we have to find out what is called as 1 by root LC. Okay, so when you take 1 by root LC, we see that it is going to be 0.2. So omega is going to be 1 by square root of 5 and 5. So that is 1 by 5, that's equal to 0.2. Okay, and so VC by VR is equal to 1 by omega RC. Just substitute and we see that the answer is still 0.2 because of all the 5s coming again. All numerical values are 5. Okay, moving on to problem number 4. we see 10 cos omega t. Omega is not shown, but the maximum value of the voltage source is given as 10. Then we have a resistor 1 ohm, and then we have 0.5 Henry. And near to terminal BB dash, from where we are looking to the circuit, we also have a capacitor of 1 farad. Okay, and the question is that in the circuit shown in the figure, the angular frequency omega, which is not given in radians per second, at which the Norton equivalent impedance as seen from the terminals BB dash is purely resistive. Okay, so again we have the same resonance phenomenon here, since the whole situation is that the frequency is such that we are having resonance, and the entire circuit becomes resistive in nature. Okay, so now we have to find out the Thevenin's impedance. Okay, what is the Thevenin's impedance? Okay, and then we'll find out omega accordingly by saying that the that the real part alone remains. All the imaginary parts are equated to 0. Okay, so what do we have here? We see that we have we start from B, go up to B dash. Okay, so that's how you pick up the Thevenin's impedance. Short circuit the voltage source 10 omega t. So that's shorted. So now we see we first pick up minus j by omega into 1, or minus j omega, and then we pick up a parallel assembly of 1 ohm and 0.5 omega. Okay, so it's going to be 0.5 j omega. So okay, so we have 1 into 0.5 j omega divided by 1 plus 0.5 j omega, and then you go for the complex conjugate multiplication and division, and finally you arrive at a value as given by 1 by omega is equal to 0.5 omega divided by 1.25 omega square. Okay, so once that is done, now it's very simple. We can solve for omega, and we can see that omega is a very very nice value. It's equal to 2. Okay, so I suppose we don't need to go for the arithmetic resolution. On the other hand, you can also try some values and see if you are just by looking at things, perhaps you'll be able to see that you can substitute for 2 in the equation. 1 by omega is equal to 0.5 omega divided by 1 plus 0.25 omega square. Why? Because 0.5 gives rise to, when you multiply by 2, it becomes 1. Similarly, 0.25 multiplied by omega square, which is equal to 4, again gives you 1. So 1 and 1, 2, 1 by 2, and then so we can say that 1 by 2. So if you just simply without solving, you can even substitute and see what the good values are, you can arrive at. Okay, moving on to the next problem. Here we have a circuit which is excited by a sinusoidal source because of the tilde mark there, and then we are having 100 microfarad capacitor in series with the same resistor R, okay, which is also which again occurs in the parallel branch, and is in series with an inductor of 0.02 Henry. Okay, and what is the question? Is excited by a sinusoidal source, the value of R in ohms, for which the admittance of the circuit becomes a pure conductance at all frequencies. Okay, we already talked about 3 different aspects of resonance. One is, of course, that the circuit becomes purely resistive. Okay, that's one thing. And the second is, of course, that the voltage and current happen to be in phase. Okay, so that's another indication. Third is the fact that when you're having, there are plenty of things, but at the same time, let's clock the third point. The third point happens to be that then the total impedance will be given by what is called as the characteristic impedance as equal to square root of L by C. Okay, so once you have such a situation, you can say that the whole circuit will be given by the characteristic the impedance root L by C. Okay, so just take L divided by the value of capacitance, and then take its square root. It comes to 14.14. That's a good value, but at the same time, I have shown on the sides in the slide the fact that you can actually replace R by root of L by C if you are having a doubt. Okay, and just at least for a revision kind of purpose, you can say that you have root of L by C plus j omega L in parallel with root of L by C minus j by omega C, and then parallel them, you will see that you will get the same resistive value of the characteristic impedance value, characteristic resistance value, which is the same as equal to root of L by C. Moving on to the 6th problem, where again we have 5 pi. So that's the maximum value. So we have 5 pi there, and then sine and then omega is 5,000, and then T. Okay, so that's the AC source, and we are having an current I coming out from there, moving into or flowing through 50 ohms and 1 millihenry. Thereafter, dividing into two, one portion goes through the 1 millihenry, the other portion goes through the 1 millihenry in series with the capacitor marked C. Perhaps we need to find out the value of C. Okay, so what's the question? The circuit shown, the current I flowing through the 50 ohm resistor will be 0. Okay, so no current has to come out. Okay, from the source of 5 pi sine 5,000 T. Okay, the value of capacitor in microfarad is what? Okay, so that's what we are supposed to find out. So how will that happen? Okay, we have discussed it earlier. We say that if you can create an open circuit due to the paralleling of an inductor with an inductor capacitor combination such that the numerical values are same, but at the same time one is positive and the other is negative, then very clearly we have what is called, then very clearly we can say that we can create an open circuit, and so no current will flow because there's an open circuit right in the middle of the circuit, so no current I can flow. Okay, so that's the idea. And how do you do that? You see that you use so the impedances need to be equated, but of course with an opposite sign, or in other words, the capacitance should overwhelm or become larger than the inductance, which are the value of which is given. So 1 millihenry means multiplying omega L multiplying by omega 5,000, you get it as equal to J5. Okay, so J5 happens to be the inductance in both circuits. Okay, so also now we need to have minus J5 in the circuit parallel to the J5 inductor. Okay, or in other words, it should be J10. The capacitance should give rise to a reactance value as given by minus J10, such that minus J10 plus J5, because they are in series, will give you minus J5. So when J5 and minus J5 are in parallel, so J5 into minus J5 divided by J5 minus J5, that's equal to 0 in the denominator. So it's an open circuit. Okay, so now we know the value of the inductor and the capacitor as equal to minus J10. Now the only thing that we have got to do is that we have to remember that it is that 10 is equal to 1 by omega C. Okay, 10 is equal to, because minus J can be discarded now. So 10 is equal to 1 by omega C, and there we can and we know omega, so we can say that 1 by 5,000 is going to give us the value of the capacitance, and when it is in microfarad, it becomes the same as equal to 20 microfarad. Okay, so let's move on to problem number 7. Yeah, what is there? There again, it looks similar because we are seeing that we are having a 10 volt source with 5 kilo radians per second, or 5,000, okay, as we saw earlier. So now we have 10 volt as the RMS value, which is of course no consequence as we saw in the previous problem. Omega is important, which is 5,000 again, and then it has a 10 ohm resistor, whereas in the previous circuit we had 50 ohms, and then J5. Okay, and then again J5 is coming on as one part of the parallel branches. The other branch having J5, and again that is an inductor of J5 and the capacitance. Okay, so now we have, okay, so the circuit, perhaps the question is also the same. In the given circuit, the value of capacitance C that makes current I equal to 0. That is, no current should emerge, or there should be an open circuit created by J5 in parallel with J5 inductor as also another capacitor. So obviously now we need to have minus J10 as the reactance of the capacitor, such that J5 is overcome, and we have minus J5 in parallel with J5. When you are having series J5 and minus J10, the total value is going to be minus J5. Okay? So you create an open circuit and don't allow any current to come out from the source. Okay, so this is a practical thing that you can do. Okay, just change the capacitor and you can have a switching in or switching out created out of this. So these are some of the practical things that you can develop by knowing really good gate problems. Okay, so now so it's back to the same old situation where you are having minus J by omega C as equal to minus J10, or 10 is the same as equal to 1 by omega C. Omega is also the same value. It is 5,000. So we have again 20 microfarad as the capacitor. Okay, so it's very similar. Okay, the 8th problem also might be similar. Let's see. We have voltage source 10 sine 100t. So there's a difference. There is a maximum value 10. There's an omega given by 100. And then we have a resistance as before 0.5. And then we have an inductance 5 millihenry. Okay, and then we have a combination of 1 ohm and a capacitance. And in the circuit shown, the value of capacitance C required for maximum power to be transferred to the load. Okay, so this is interesting because we now we need to have a maximum power transfer to the capacitance. Okay, and we need to find out the value of the capacitance. Okay, so now we have we have, let's see, let's look at remember the maximum power transfer theorem, which says that if maximum power has to be transferred to the circuit here, it should be equal to the Thevenin's impedance. Okay, or in other words, you had better realize that since the input resistance is 0.5 ohms, and then you are having J5 millihenry there, by 5 millihenry, or 5 into 100, or 0.5 J inductance there, then the inductor and the capacitance together, the resistance and the capacitance together should create a complex conjugate impedance in series, such that maximum power transfer theorem can be satisfied. Okay, so that's what is shown here. We have what is called as a situation wherein 0.5 ohm plus J5 ohm, that is the resistor and the inductor at the beginning of the circuit, should be supplemented by a pair of elements. First is, of course, the same old resistance 0.5, and then the complex conjugate of the imaginary portion of the impedance, that is 0.5J. It should have its conjugate as minus 0.5J as the impedance value for the capacitor. And how can this be true? Okay, so of course you can now substitute for the imaginary portion, and you can and the real. Okay, so I have substituted for the real portion, and I have found out that it's equal to that. That's equal. That is, the value should be equal to that is it has been replaced, and then it has been and the value has been calculated as equal to 10 microfarad. Okay, so that's 10 millifarad. That's on one side. On the other hand, you can also remember that if you are having a real and an imaginary element, not an imaginary element, an element with a J value there. Okay, it's not an imaginary element; it's a capacitance. Okay, so if you are having such two such elements, one is real and the other is with a J value there, then you can and they are both the same. Okay, that is 0.5 and 0.5J. In that case, you can say that the parallel combination is going to be something like and that double of it. So if this is 1 ohm, the other will have to be again 1 ohm. Okay, so in that manner also you can calculate, and that's how it has been done on the right hand side. Since XC is minus J 0.5 after paralleling with 1 ohm, before paralleling it is the same as equal to XC is equal to minus J1. Okay, so now if the XC is equal to minus J1, you can easily without going for the equating of the real or imaginary portion, you can calculate, since you have already got it as equal to minus J1, that is 1 is going to be the 1 is equal to 1 by omega C. So just so C is going to be 1 by omega, and omega is equal to 100. So again we can say that it's 10 millifarad. So two ways of doing the same problem. The second method is easier. Both are given in the slides. Okay. So moving on to the 9th problem. Okay, we have more problems in AC because there are more problems come for gate examination. Okay, so we have again VT and Z looking into the terminals, where we see VT is the applied voltage across AB. We see IT flowing through an inductor. Then we have a capacitor of 100 microfarad and a resistor in parallel to it as 100 ohms. Okay, and what is asked out of us is that, okay, we are using all the ideas that we have been collecting so far. Okay, so when you are having two elements in parallel with equal numerical values, but one is real and the other is with a J component, or which in mathematics is called as imaginary, then half of these values will come as in series. Okay, when we are having them in parallel. Okay, so now we are having two elements in parallel. Let's see if they have equal numerical values. Okay, so we have the voltage VT across the terminals A and B, as shown in the figure, is sinusoidal voltage having a frequency omega. So once omega frequency is there, we can compute the value of the reactance of the capacitors to see if 100 ohms is getting in parallel with it minus J100. Okay, in that case, we can just simply write it as a series component with 50 and minus J5. Okay, I hope you remember these were things that we discussed right at the beginning. Okay, in the structure of the network. Okay, so we have, so now it's going to be 1 by omega c. So 1 by 100 and 100 and 10 raised to minus 6. So we see that it's the same as equal to again another minus J100. Why? Because it's a capacitor. So when you are having minus J100 in parallel with 100, it's going to be in series, elements will be 550 minus J50. Okay, so that portion is over. Now what is asked is when the inductor current IT is in phase with the voltage VT. Okay, so if the inductor current has to be in phase with the voltage, in that case, we must realize that the inductor should cancel out, the impedance must cancel out the series impedance, which is minus J50, or in other words, it should have a reactance value as given by J50. Okay. When the inductor IT is in phase with the voltage VT, the magnitude of the impedance in C between the terminals A and B is. So now my J plus J50 plus 50 minus J50 is going to, all of them are in series, because the parallel version we have converted into a series version where we are having 100 and J minus J100 as in parallel, converted to two elements in series. One is 50 ohms, the other is minus J50 ohms again. Okay, but of course one is resistor, one is the contribution from the capacitor. Okay, so now we have only 50 ohms is left. Okay, you can calculate the value of the inductor also very easily, because now we know that its reactance is J50, which is equal to omega L, and omega we know is equal to 100. So it's very simply 50 is equal to omega into L, or 100 into L. So 100 can be utilized, and if required, you can calculate the inductance value also, as we have been doing so far. Okay. Now 10th problem, it's also simple. The current in the circuit shown is what, and another important aspect has been shown here. It's a very simple problem, but realization has to come. So the fourth point is now added. It's a series circuit, and the voltage across the inductor as also across the capacitor are seen to be equal. What does it mean? It means that the impedances are equal, and they, since though the impedances are equal, one is positive, the other is negative. One will be Jx, the other will be minus Jx. Okay, equal values, and that's the reason why we have resonance there. And so the only element that is functioning in the circuit without the only is resistive essentially. Okay, so we can see that the 20 ohms remains, and the inductor and the capacitor, the impedances cancel themselves. Okay, because there is resonance. Okay. As evident from the fact that the voltages are equal. Okay, the current in the circuit shown is, so it's simply 100 divided by 20 ohms gives us 5 amps. Okay, very simple problem, but fourth point has been added as to how to diagnose or how to use the phenomenon of resistance. Okay, so moving on to the 11th problem. At very high frequencies, the peak output voltage V0 in volts is what? Okay, so very high frequency. What does very high frequency tell us? It tells us that all capacitances will have 1 by omega, where omega goes towards infinity. So all the capacitances will function as short circuits. So the top and bottom capacitors are shorted out, and then the middle it's of course a Wheatstone bridge, otherwise also it will shorten out, and so we need to find out only the voltage across. We need to find out the voltage V0. Okay, so what is that? So 1 sine omega t is applied, and then we are having 1 and 1 in parallel, and again 1 and 1 in parallel. Okay, and so what do we see? We see that we are having half and half, and so the whole voltage is divided into 2. That is half, and what is asked is the peak output voltage. So very simply, the peak is 1, so half of it is given as output, because we are having equal resistors creating the potential divider. Whether the 100 microfarad in between is a short or an open, it does not matter, because the output voltage is half of the whole lot. Okay, and the two capacitors that we have at the two terminals of the source happen to have shorted out because of very high frequency. Okay, so that's also a simple problem. Now let's move on to problem number 12, where we have an inductor of 0.1 Henry, and then we are having an inductor and a capacitor and the resistor in parallel. Okay, and the resonant frequency for the given circuit is asked. Okay, so here I will tell you how to do it, and then I will also try to help you to tell you how to do it in a very easy manner. Okay, so right now the method is that you take out the impedances completely. So the first quantity is 0.1 j omega, and then you are having added to it the parallel combination of resistance and capacitance as given by minus j by omega into 1 divided by minus j one. Okay, so it's okay. So I hope the formula is clear to you. It's going to be the omega has been taken downward. Okay, and capacitance value is equal to 1. So minus j divided by omega minus j. Okay, so now we convert it into to convert it into real imaginary portions. You have to multiply and divide by the complex conjugate. So now it's easily 0.1 j omega is equal to minus j omega plus j divided by omega square plus 1, because you have multiplied and divided by omega plus j. Okay, so we have in the denominator you have omega square plus 1, and on the numerator you have omega plus j. Okay, and then you are supposed to equate it to 0 to find the resonance frequency. And so you'll see, if you equate the real parts, you'll see that the frequency is equal to 0. Okay, that's good, because it's telling us that that it is talking about a DC equivalent, which is always going to be there. Okay, DC frequency which is equal to 0. Okay, another is equating the imaginary part, you will find omega equal to 3. Okay, another way that you can do is that when you are having a resistor as small as 1 ohm in parallel to 1 farad, you can easily you can try to see that, okay, very small ohmic value, then you can consider that 0.1 Henry and 1 farad are in series. Okay, and you can see that you can simply find out 1 by root LC. Okay, so that will also give you the frequency value as very near to 3 radians per second. That's enough, because when the resistor gets parallel to it, then you get the exact value as equal to 3 radians per second, as was mentioned earlier. By imagining by equating the imaginary parts, you will get omega is equal to 3. Okay, very correctly you will get 3. Okay, because right from the equation you can see that it's possible. Okay, so because 0.1 j omega is now going to be equal to minus j omega, or is going to be equal to j omega by omega square plus 1. So j and j can be removed. So it's going to be omega cube plus 0.1 omega cube plus 0.1 omega is equal to is going to be equal to equal to omega. Okay, so now it's so 0.1 can be taken to the other side, so it's going to be 0.9, and then divide by 0.1 such that you can omega cancel, so you can get omega square is equal to 9. So and then so omega is equal to 3. Okay, yeah. So now we move on to the last problem in this session, where we are seeing that a series LCR circuit is operated at a frequency different from its resonant frequency. Okay, so it's a different situation, but resonant frequency is mentioned. The operating frequency is such that the current leads the supply voltage. Okay, so leading the supply voltage is also important, or in other words, the capacitive effect is prominent. The magnitude of current is half the value at resonance. So resonance is a situation wherein the current is double the current which is now applicable to the operating situation. Okay, operating frequency is different from the resonant frequency. Okay, if the values of L, C and R are all 1 Henry, 1 farad, 1 ohm respectively, the operating angular frequency, okay, which is different from resonance, is what is asked. Okay, otherwise you could have easily taken the square root of 1 by root LC, or you could have taken the 1 by LC, or 1 by root LC would have given you the resonant frequency. Okay, so that's not the situation. We have to realize that when resonance was happening, the impedance was equal to R. But now what has happened is that the current is that current is double the current at the operating frequency, which is not the resonant frequency, or in other words, the impedance has doubled. Okay, or the new impedance is going to be equal to, because the current has halved, so impedance has doubled. So now the new impedance is, and that is the operating frequency. At the operating frequency, the impedance is going to be 2R. Okay, so that's one part. And so we see that. Okay, so we see that we are having what is called as so to get to R. So R is equal to 1. So the total value is equal to 2. So how do you get 2? By square root of Z square minus 1. 1 happened to be the square value of resistance of 1 ohm. So that's equal to root 3. So now X value is equal to root 3. Okay, and that is created out of two quantities. One is 1 by omega C, and another is 1 by omega L. They act in opposition to each other, but the predominant component is capacitance, because the current is leading. So 1 by omega C minus omega L is equal to root 3. So you can find out omega from here by, of course, multiplying throughout by omega C. C is 1, L is also 1, and then solving the circuit, you see that omega is equal to 0.457 radians. As simple as that. And I suppose you have noticed certain aspects that we have talked about resonance. At least 4 points were discussed. That is, the circuit becomes purely resistive, and so only resistance remains, the rest can keep. At the same time, the voltages across the inductor and the capacitor in a series circuit cancel. Okay. Third is of course the fact that there is a that the current and voltages will be in phase. Fourth point that we had better remember happens to be that then the whole situation can be replaced by the characteristic impedance as given by root of L by C. So whether it be parallel or series, based on whatever we understand, we can go forward. And the resonance frequency is given by 1 by root LC, especially for a parallel situation, as also purely parallel and a purely resistive kind of situation. Okay. The rest, of course, by equating the real and imaginary portions, you can go forward. Okay. So thank you.